In this video, I'm going to talk about some of the tricks that Infocom used to make their games the killer apps of the 1980s and how we are still using those tricks today. In a previous video, I talked about CPUs, and a CPU is designed to execute instructions. When you turn it on, it falls into the cycle of fetch, decode, execute. Fetch, decode, execute. It reads the next instruction to execute, it figures out what it does, and then it carries out that instruction. So the CPU is reading from memory, and it's also writing to memory. So that's what a CPU does. It just reads an instruction, executes it, and maybe that instruction makes it right back to the computer's memory. But I never really talked about how do we get these programs that the CPU runs. So the CPU executes a program that's in binary. It's in ones and zeros. That's what the CPU does. It reads ones and zeros and it writes ones and zeros. But we don't write in ones and zeros. So how does that work? Well, we need some tools for that. So we usually write in a high-level language, C, C++, Java, Python, something like that. And we use a tool called a compiler. And that compiler turns your high-level code that's in a modern language down into something called assembly language. The assembly language is very close to what the CPU actually executes. And then we use another tool called an assembler to convert that into a binary file that has ones and zeros. So no matter what development environment you're using, when you build your program, there's probably a compiler and an assembler under the hood that are taking your code that is maybe slightly English-like, and it's crushing it down into the ones and zeros that a CPU can actually execute. Now, the downside to this approach, though, is that these ones and zeros are specific to a type of processor and probably specific to a type of computer architecture as well. So this file that you've now built for Windows can't go run on a Macintosh, or if you built this on Linux, it's not going to go run on Windows. So we've compiled this program, but it's not portable. We can't take this and just kind of run this anywhere. But that's how we take a program that written in a high-level language and crush it down into ones and zeros that a CPU can actually execute. So let's do a little thought experiment here. Could we make a program that pretends to be a particular CPU and reads and writes from some memory that it's been allocated? Could we make like a piece of software, a program that pretends to be a particular CPU hooked up to memory? Yeah, absolutely. I mean, that's what an emulator is. We could, and we use emulators all the time, particularly for playing games. So we can take a CPU and that's hooked up to memory, and we can emulate that using software. We can make a program that pretends to be that CPU. So just keep in mind, we use emulators all the time. An emulator is just a program pretending to be a CPU hooked up to some memory and probably some, a sound card and graphics card and some peripherals or something like that. Okay, now here's a thought experiment. If we're going to make up a program that pretends to be a CPU, did that CPU ever actually have to exist in the first place? Like, could it just be some CPU that somebody designed on paper that was like optimized, particularly good at doing, tackling a certain type of problem? Could it be an imaginary CPU? Well, yes, we could. We could make up a CPU architecture that's optimized for a particular type of program, like say an adventure game, and we could make a virtual machine or a program that pretends to be that. You could think of it as an emulator for an imaginary CPU, a CPU that doesn't exist in the real world. It just exists as a concept, and we make a program that pretends to be that CPU. I know this is getting kind of weird, but this concept is called a virtual machine. And this is a very, very important topic, or very, very important concept in computing, a virtual machine. It is a piece of software that pretends to be a particular CPU, and it can execute any program that has been compiled down into the ones and zeros that it understands. So here it is, kind of formally stated. A virtual machine is a program that pretends to be a CPU and can run programs compiled into the machine language, the ones and zeros, that CPU is designed to understand. You can think of it, it's like an emulator for a piece of hardware that only exists on paper. So this is what Infocom did, and we'll explain like why would they do this, like why would they go through all this extra work. What's required, but like why would they do that, and how is that relevant now? Well, let's go back and revisit how like what we have to do to make a program. We make a compiler and an assembler, and we have a high level language, and the compiler and assembler crunch a program down into the ones and zeros that a CPU understands. So what we need to do here is, if we make up a virtual machine, we kind of invent a new CPU, we have to invent, like we have to go write a compiler and an assembler that'll take some language and crush it down into the ones and zeros that our virtual CPU understands, that the virtual machine understands. So rather than having a compiler and an assembler that target a real piece of hardware, they're going to target this imaginary piece of hardware. So just to recap here, if you invent a virtual machine, you have to also invent the tools that will allow you to compile a program to run on that virtual machine. But why would you do that? Like, why would you care? What's the advantage of this virtual machine thing? And that's because you could write a program once and run it anywhere that virtual machine is installed. And we're going to take a look at why this is a big deal for Infocom, why they would go through all this trouble and build this revolutionary Z machine thing that they do. Like, why would they go through all the trouble? Well, let's just make sure we understand what's going on here. So if we have a program that's written for a virtual machine, if somebody's written the virtual machine for the Mac, it'll run on a Mac. If they've written it for Windows, there, fix the slide. It'll run on Windows. If that virtual machine exists on Linux, you can run it on Linux. You can take that program and run it on any computer, any type of computer that has that virtual machine program implemented. So you could think about it like Java, like you can take your Java program and run it on any machine that has the Java virtual machine installed. You can take your Python program and run it on any machine that has the Python interpreter installed. So you get to, with a virtual machine, you get to write your program once and run it anywhere that virtual machine has been implemented. Now let's go look at Infocom's situation in the 1980s. In the 1980s, the computer landscape is very different from what it is today. There's a bajillion types of computers out there that are all long gone, all extinct, that were all popular but mutually incompatible. So it's not like you're just trying to write your game for Windows, which became the dominant platform. It's like you had to support all of these different platforms. So what were you going to do? Were you going to write a different version of your game for each one of the 20 different types of computers you were going to support? No, it would make sense to do this virtual machine approach. You build one version of your game, and then you write a program that can run that virtual machine on each one of those target platforms. Now, I know that still sounds like a lot of work, and it was, but it was much more efficient strategy. So just to kind of backtrack here and clarify like what they actually did, Infocom designed a CPU designed for running adventure games, and they called it the Z machine. Z was for Zork. Zork was their first game. It was the test bed for all of these tools, the Z machine. That is their virtual machine architecture. They designed a programming language called ZIL. ZIL was a language designed just specifically for writing their adventure games, and then they wrote a compiler called Zilch, the Zork Zork Implementation Language Compiler Hack. That's what it was. Zilch was their compiler. So Z Machine was the fake CPU, the virtual CPU they designed. They created a language called ZIL, and they would use Zilch to crush it down into Z code or Z machine code. Now, to run that game, all they had to do then was write a Z machine interpreter for the different computers that they wanted that game to run on. So imagine you have a library of 40 games that you've written, and somebody says, hey, can you support a particular new computer? And you just go implement the Z Machine for that platform, and all of those games will now run on that platform. And the minute you write a new game, it'll run on any computer that has the Z Machine interpreter, that virtual machine. So you get this write once, run anywhere thing. And back in the 1980s, that was particularly important because there's so many different types of computers. I'm just going to say this again. What does a virtual machine get you? Write once, run anywhere, right? Java uses the same approach. You build your Java program, it compiles down to the Java virtual machine, and you can run your program anywhere the Java virtual machine exists. And that's Java was designed to for the same reason, because it was designed to run on like cable modems, routers, whatever. Who knows what type of processors in there, but we're all going to just implement the Java virtual machine for them, and we'll do write once, run anywhere. So I think my slides might have gotten out of order here, but here's their build process. They would write a game in this Zork implementation language, compile it with Zilch, and that would compile down to Z machine code or Z code, and that could be run by a Z machine interpreter. And they just wrote Z machine interpreter, which is not a hard thing to do for all the bajillions of computers they wanted to support. And then the entire library of games would run on that particular computer. So the virtual machine gets you write once, run anywhere. Now, like, how has this been, why was this important historically? Why? Well, we can still play these games today. And why can we play them today? It's because, well, they weren't designed to target a particular machine. They weren't compiled down to an Intel 8080 or a MOS 6502 or a Motorola 6809, or they weren't targeting any particular computer. They were designed to be run by this virtual machine. And people reverse engineered this thing. And anytime somebody invents a new machine, they just rewrite the Z machine for it. They re-implement that virtual machine, and now the entire library of Infocom games will run on that machine. So that is why we're still able to play these games. You can play them on Windows, Mac, Linux. You can play them on your phone. It's because they're running in this virtual machine. This virtual machine has allowed these games to survive, where many other games that were just sort of compiled for a particular platform have died and have been forgotten. Now, if this virtual machine exists, could you invent a new language to target it? Yes. Now, it's worth talking about that this ZIL language that Infocom made it's a god awful language. It's absolutely horrible. Like I can't read it to save my life. But could you come up with something better? Like absolutely. So there's now a language called Inform that you can use to make adventure games that will build your game down. It'll compile it down to Z code so you can run it anywhere. I have reviewed this language, and I also find it to be horrible, and that is partially why I have spent so many years working on Lantern, because I think Lantern is a much easier, user-friendly system for making adventure games. But Inform is the 8,000-pound gorilla of adventure game languages now, because you can write a game and run it anywhere using Infocom's virtual machine. All right. Now, also, what happened to the original source code for all these Infocom games? Well, it turns out people thought they were lost to history, but somebody actually saved them on a hard drive and then eventually passed them on to Jason Scott, who runs archive.org, or the Internet Archive. So now we actually have the original source code for all of these games, the ZIL code. Now, unfortunately, ZIL is just, again, it's a god-awful language. It's very difficult to understand. But there are now people actually trying to write adventure games in ZIL and compile it using Zilch and run them using the virtual machine as people would have done in the 80s. I think these people are crazy, and I, as a programmer myself, I want to take advantage of modern tools to make my games for old machines. But there are people out there who just insist on doing it old school. Okay, so just to recap, virtual machines are everywhere now. This was very cutting edge in the early 80s when Infocom did it, but virtual machines are all over the place now. because of this write once, run anywhere. And this is particularly important because so much stuff is web-based and you're deploying your code to servers and you don't want to know or care what kind of processor they have in them. So Java and Kotlin, which is a relatively new language, they compile down to Java bytecode and they get run by the Java virtual machine. Microsoft has its own virtual machine, the Microsoft Common Language Runtime. So Visual Basic, C#, F#, that's supposed to be F#, not F$. Those languages compile down into a format that is run by Microsoft's virtual machine. And you can think about Python as a little bit, somebody will get on my case and say Python's not exactly the same thing. And it's not, but it's that same idea of you can take your Python program and run it anywhere where there's a Python interpreter. So virtual machines are very, very important because they give you this ability to write your program once and run it anywhere. And that is a very, very huge, that's a huge convenience in the modern world. But in our particular case, it's very, very important because it has allowed this library of masterfully crafted adventure games to survive into the present day where we can still enjoy them.